All right. So chapter 4 is where we're finally going to start diving into how we graph all of these different trig functions that we've learned how to do algebraically all semester long so far. So you don't have to have graph paper or anything like that. Obviously, all your assignments are on the computer outside of our tests. If you like your notes to look extra nice, you might want some graph paper, or they make graph sticky notes or graph note cards. Those are also nice to have. I did make a handout, which I gave to you. This is just so you could have the general pictures of the sine function and the cosine function. And then on the back of that paper is how we are going to graph these. So I tried to give you some of that so that you have a general picture to go off of and reference as we move forward. Because today we're going to talk all about sine and cosine functions, how we graph them. And then 4.2, the very next section, is how we translate those and move them around and stretch them and shrink them and flip them and all kinds of other stuff. If you've had college algebra, the next section, 4.2, is very similar to 2.5 from college algebra. 2.5 in college algebra was all about translations of functions, and that's where we learned about reflecting it across the x-axis. It's where we learned about vertical shifting and horizontal shifting and all that kind of stuff. We get to do all of that same stuff with our trig functions. So if you need reference to that, if you haven't had college algebra, if it's been a hot minute since you've had it, go to the YouTube site where all of these lecture videos are and look at either my Missouri Southern 2.5 lecture or my Pitt State 2.5 lecture. Both of those cover translations of functions and give you a nice overview of the stuff that's in 4.2. So, periodic functions. A function f such that f of x equals f of x plus np for every real number x in the domain of f, every integer n, and some positive real numbers. P. The least positive value for p is the period of a function. Periodic functions repeat. That's what it means to have a period in terms of mathematics, is that there's a certain window or period that it takes our graph to go through an entire, I don't want to say rotation, but an entire, it's a period. Like it takes a certain amount of time for each of our graphs to do one full rotation, I guess, of sorts. And that period is something that's going to be very important because that tells us how far we are going to graph it over. There's a star note there that says the circumference of the unit circle is 2 pi, so the period of sine and cosine is also going to be 2 pi. In order for us to look at the entire range that happens within these periodic functions, it takes the entire 2 pi range. So the first of these functions that we were talking about is our sine function. And I'm just giving a lot of notes about it. I give the basic graph of these so that when we have to graph them ourselves, we have a starting point. The sine function has a domain of negative infinity to positive infinity. This goes on forever in either direction. It continues to do the wiggle all the way across. You can find a sine of any real number. Thus, the domain is negative infinity to positive infinity. But the range is limited because we only go up to 1 and down to negative 1. The function of sine is symmetric to the origin, and it is an odd function. Again, some of this makes more sense if you think back to your college algebra days, where we talked about odd, even, and neither functions. An odd function means that if you plug in negative x, you get the same thing out as if you had a negative outside of your function. That's what this means here. Again, this is from Chapter 2, College Algebra. So I did give you a picture of the sine function here in my notes, but I also made it on this handout so that you can see what happens as you move along your sine function. Something that I thought was very interesting, and so I made sure to include it on your printed handout as well, is this graph, which is how the sine function is actually connected to our unit circle. Because we spent a lot of last chapter and last sections talking about this unit circle. And I told you that if you memorize some of the unit circle, it would be very helpful to you. And the sine function, or the sine values, were always our x's. Our y values on our unit circle. Remember, each of our values on our unit circle was made up of our cosine and our sine. this right up here coordinates and shows you how our sine wave is related to our unit circle. It also helps it to me at least, visually picture why our range is limited to 1 and -1. But when you go around the unit circle, the highest value that your y's ever achieve is 1, and the lowest value that your y's ever achieve is -1. And so all of this is just another way of representing it over here with our actual wave graph. So the domain is the angle measures or the arc lengths, and the range is your y-coordinate or the sine values themselves. And so I found that really interesting. It all does tie in together. The stuff we learned last chapter is just as applicable now that we're going to actually be graphing these. So this picture is the same one that's the middle picture on the handout that I gave you guys. When I found this picture, I decided I wasn't going to try and make you guys copy that down really quick because it's got a lot of details in there. But I liked the side-by-side representation of the unit circle with half of the sine wave. All right, I'm going to flip over. So one thing to note, which I can pull them up side by side here, is that our sine wave, if we're starting at 0, it starts at 0 and then it goes up and then down. And if we move to the left, it goes down and then up. If we look here, when x is 0 for cosine, we're starting at the 1 and then we come back down, going either direction. So our cosine looks a little bit more like a W. Again, I give you lots of, general information about our cosine. And cosine is the bottom graph on the handout that I gave you. The domain, again, for cosine is going to be -infinity to positive infinity. The range is, once again, -1 to 1. But this is symmetric to the y-axis. When you're symmetric to the y-axis, what that means is if you fold your graph in half along the y-axis, everything from the right would lay right on top of everything on the left, and vice versa. This is an even function, which means if you plug in -x, you're going to get the same thing out as with positive x, which you can see that in the graph. Because if I'm looking at -pi/2, I'm at 0. And if I'm looking at positive pi/2, I'm also at 0. It doesn't matter if it was negative or positive. I'm getting the same output. That's what it means to be an even function. So the big thing to note is that if you're thinking at least in terms of where you're starting with your graphs, the sine function starts down and goes up, down, up, down. The cosine function starts up and comes down, up, down, up. When we are graphing these, we are going to talk about something called the amplitude. That's probably a new term unless you've had some sort of trigonometry class in the past. The amplitude is our range, basically. And if our A that's in front of it, which you're going to see a very general form of the equation here in just a minute, but if your A is 1, then your range is -1 to 1. What happens, though, is we're going to graph more complicated functions and equations. And so this A that can fall right here in front of your cosine or right here in front of your sine can be different values. And whatever those values are tells you your amplitude. what this is actually connecting to, let me shift over just a tiny bit, is right here, College Algebra 2.5, which I've already mentioned once before. It's the vertical stretching and shrinking translation. So in college algebra, we learned that if that letter out in front is a fraction, then what happens is our graph shrinks. If it's between 0 and 1, our graph gets smushed together. It's not rising as fast. If that number out front is greater than 1, what happens is it stretches our graph vertically upward, and so things grow a lot quicker. And so this amplitude, while it's giving a new term and a new name here in trigonometry, is just another way to examine vertical stretching and shrinking that happens within our functions. You will be asked to identify the amplitude of these various functions as you work through them. The amplitude does affect your range, as it shows there. You're going to take the absolute value of whatever your amplitude is, and you'll have your range go from negative, the absolute value of that amplitude, up to the absolute value of that amplitude. So like I said, when you're just dealing with y equals cosine or y equals sine, then your a is 1, so your range stays between that -1 and 1. I'm going to slide it up a little bit and talk about the period. Because amplitude and period are the two big things that you're going to be asked for when you are getting ready to graph either sine or cosine. Your period is what I mentioned earlier, where it takes you like the whole time to get through one of the graphs. So this is our b, and it says for b greater than 0, the graphs y equals sine b of x and y equals cosine b of x will resemble sine x and cosine x respectively, but with a period of 2 pi divided by b. So notice that those b's are inside of the functions themselves. So those of you that are taking college algebra right now alongside, this is actually one of the times where it is beneficial, because hopefully you've just had the translation section, or you're getting ready to. I know my students have just had it. And so you can think about that b is inside the function, and when the b is inside the function, it's the same thing as a horizontal stretching or shrinking. And horizontal stretching or shrinking translations actually do kind of the opposite of what you would think would happen, meaning that if b is greater than 1, so if it's a whole number greater than 1, or anything greater than 1, what happens is horizontally our graph actually gets shrunk. It gets smushed together. Maybe you can understand that because our period is 2 pi divided by b. So if b is 4, then our period is going to be pi over 2 instead of 2 pi. It shrunk our period down. It smushed it together. The flip side of that is if b is between 0 and 1, so it's a fraction, then what happens when you divide by a fraction? You have to flip it and multiply. So if b is a half, then what happens is I have to flip it and multiply it. So then instead of taking 2 pi to get through a period, I'm taking 4 pi to get through a period. So I've taken my graph then and I'm stretching it out over a longer period of time. So amplitude refers to vertical stretching and shrinking. The period refers to horizontal stretching and shrinking. Amplitude affects your y values, your outputs. The period affects your x inputs, because you're going to either stretch them out over a longer period of time, or you're going to smush them down into a shorter period of time. Are there any questions so far about any of it? There's a lot of notes up front, and then we actually start graphing these, and you'll get to see how they work. This last section of notes before we actually start graphing them, you actually have. You can write them again. If you flip over the paper that I gave you, I did put the table that these are all in on the back of that, so that you would have them. This is how we're going to approach graphing our sine and cosine. And notice it gives the general form y equals a sine b of x, or y equals a cosine b of x, where b is greater than 0. So we could have vertical stretching and shrinking, thus our amplitude could be there. And we could have horizontal stretching and shrinking that affects our period. So before you ever start graphing any sine or cosine function, the first thing you want to do is you want to find what is the period of your function. That's 2 pi divided by b. You're going to start with 0, and then you're going to lay out a distance of 2 pi divided by b. And then you're going to divide or subdivide that section into 4 equal parts. This sounds weird. You're going to see it. It makes a lot more sense once we actually work an example. But we divide that interval into 4 equal parts, and that will give us some x values to evaluate our function at. Each of those 4 values we want to plug into our function and get an output for. We are doing a trigonometric form of plug-in chud or point plotting system. So back in college algebra, one of the very first ways you learn to plot or graph any equation ever is the point plotting system. That's where you put in a bunch of x's, you plug out a bunch of y's, you have your ordered pairs, you plot them, you connect the points. That's how we do this with our sine and our cosine functions as well. Once we have evaluated our function at those different points, we put them on a graph and we connect them. Are you ready to try one? Lots of notes up front. Now we actually get to apply them. We're going to graph y equals 2 sine of x. So the very general form was y equals a sine of bx. This a told us vertical stretch and shrink, and the b told us the horizontal stretch and shrink. The a, one of the reasons I think it's probably shortened with a, affects our amplitude. The b affects our period. So the very first things you want to find is you want to find the period of your function, you want to find the amplitude of your function. Okay? So the period of our function is going to be 2 pi divided by b. Well, what is b in this function? 1. So that means our period is 2 pi. Our amplitude is going to be the absolute value of a. What is a in this function? 2. So the absolute value of 2 is 2. So this one's going to be slightly vertically stretched compared to our basic function because our amplitude is 2 instead of 1. So we will have some vertical stretching going on here. So I made a note that our graph, you don't have to write this, but if you want to, is the same as y equals sine x, but with a range of -2 to 2, because that's what our amplitude does. It affects our range. So if you know, which you don't, I'm not expecting you to know the graph right off the top of your head or anything like that, but if you know what the basic graph of the sine function looks like, then all you have to do is slide up the y values as you move through this. And because I had graph paper, I'm going to show you my graph that I actually made in my notes because it looks better than anything I'm going to be able to just whip out here. And I'll zoom in. Maybe focus. Okay. So what I did is the red graph, the slightly smaller looking graph, is just part of the main mother function, as we call it. It's y equals sine of x. That's your red graph, going from 0 to 2 pi. The green graph is the actual function y equals 2 sine of x. Notice our x values don't change at all. The only thing that changed is our y values, because we have amplitude of 2, so it goes up twice as far as the original function. Because this one only affected the amplitude, I didn't do all of the steps in our guideline for sketching the graphs. Because to me, it was a lot easier to just look at the basic graph and then pull it up and pull it down. Most of these, I think, are multiple choice. I'm not totally sure on that. But a lot of times, I know in the college algebra section for translations of functions, what they do is they give you like 4 to 6 graphs and they ask you which one is correct. The other thing they can have you do is you actually do graph the function, but what happens is you graph the main function. So you would graph like the red function, the y equals sine of x, and then you tell the graph what kind of translations are going on. You would tell them that you have a vertical translation or a horizontal translation, and then the graph does it for you. You don't have to actually plot the individual points and then connect them on the computer program itself. When it comes to a test, you will actually like manually draw them in. Okay. Ooh, I forgot I zoomed in. Sorry. Zoom back out. Let's look at a cosine one. This one we will actually do all of our steps. Graph y equals cosine of 2/3 x over 1 period. So first things first, let's figure out what the period is. Period is 2 pi over b. And especially while you're still learning the difference between periods and amplitudes and all that kind of stuff, write down these general forms. It's very helpful to identify what's going on. Our b in this case is 2/3. So that's 2 pi over 2/3. That's the same thing as saying 2 pi times 3/2. Notice our 2's would cancel out, meaning the period for this function is 3 pi. So we are definitely doing some horizontal stretching here because instead of our graph taking up 2 pi, it's now going to take up 3 pi. Our amplitude is the absolute value of our a. That's the number or the coefficient in front of the cosine. There isn't one, which means our amplitude is just 1. So there is no vertical stretching or shrinking for this one. Step 2 on our list for sketching the sine and cosine says we have to split up our period into 4 equal sections. So what we're going to do is we're going to start with 0, and then we're going to have 4 individual sections. Divide 3 pi into 4 intervals. So that means we start at 0. Our next interval will be 3 pi divided by 4. And then 3 pi divided by 2. 9 pi divided by 4. And 3 pi. You always want to start with 0, and you want to end wherever your period is supposed to end. So when we had our period was 0 to 2 pi, then we would have pi over 4, and then, pi over 2. And pi, and then 3 pi over 2. You want even intervals, even sections. So what good does this do? Well, we're going to do our fancy plug-in and chug-in. And for this, I usually make a table. Our book uses a table, and I think it's nice. It's not like some complicated table. All it does is it helps us keep track of what everything equals. So x, that's going to be these various values that we just found for our intervals. So x is going to be 0, x is going to be 3 pi over 4, 3 pi over 2, 9 pi over 4, and 3 pi. Those are our x values. Those are what we're going to plug into our function to figure out what's going on so we can graph it. The next thing you should find is notice that we're not taking x, we're taking 2/3 times x inside of our function. So we're going to do 2/3 x. Well, 2/3 times 0, 0. 2/3 times 3 pi over 4 will give us pi over 2. And you keep going all the way down. On our little table. So the top row is just our inputs. That's the different intervals that we're cutting our graph into. The next row takes into account that we have 2/3 times x inside of our function. The last one is where we're actually going to compute the cosine of the 2/3 x. And the reason why I like the table so much is I'm not trying to find, well, 2/3 times this and then find the cosine of it. All I need to think about is what's the cosine of 0. And that's what's going to go in this spot. And if you don't know what the cosine of 0 is, you can always use your calculator. But this is one of those reasons that memorizing at least sections of the unit circle is very helpful. Because if you know what the unit circle is, then right off the top of your head, you should be able to tell me what the cosine of 0 is. And it's 1. Because that's your x value over there at 0 on your unit circle, which is at 1. And then you're being asked for cosine of pi over 2. That's the cosine of 90 degrees. That's 0. The cosine of pi, that's -1. 0, 1. This bottom row is the information that we need in order to graph. These are our y values, and our x values are up here at the top. We have just made ordered pairs to be able to graph our cosine. Again, I think my graph here is going to be better because it's on graph paper. So I'm going to zoom in so you can see it on here. So notice from my graph, I start at 0, and I go all the way out to 3 pi. And the little breakups on here are these x's that I found, my interval breaks, at 3 pi over 4, 3 pi over 2, 9 pi over 4, and at 3 pi. And then I plug in the values that I computed when x is 0, my y or my function's at 1, and then 0, -1, and so on. This is a cosine function, so I start it up, and I go down, and I come back up. Are there any questions on any of those first two? The first one just had a change in amplitude with our sine function up here. The second one only had a change in the period. It didn't have a change in the amplitude. So our next one is going to have a change in both the amplitude and the period, so we can see what happens when both are at play. Flip it over. I strongly recommend going back and looking at the College Algebra 2.5 stuff. It is very helpful. Remembering and refreshing yourself on these translations of functions. We're going to graph y equals -2 sine of 3x over 1 period. So let's find the period. Period is 2 pi over b. Remember that the general form is y equals a sine bx. So the b in this case is 3. So 2 pi over 3. So we are shrinking and squishing our graph horizontally. our amplitude is going to be the absolute value of A. A in this case is -2, so the amplitude is +2. That just tells you our range. That means we are going to do some vertical stretching with this as well. So vertically we're stretching it out, horizontally we're smushing it in. Now we need to divide our period into four equal parts. So we need to divide our 2 pi over 3 into 4 equal intervals. If you're not great with fractions, this is a good opportunity to start mastering those again. Because we're going to start with 0, and then we need to take 2 pi over 3 times 1/4. And we'll need to take 2 pi over 3 times 1/2, which is the same thing as 2/4. And 2 pi over 3 times 3/4. That's the algebra we're doing in order to find these different intervals. And then we end with the 2 pi over 3. So we get comma, pi over 6, pi over 3, pi over 2, and 2 pi over 3. That's how we're going to subdivide our period, and those are going to be the x values that we're going to put in to our graph and into our function to figure out our outputs. So let's slide up. Now I'm going to make a table. Do you have to make a table? No. You do not have to make a table. And if you don't want to make a table, you don't have to. I really like the tables for keeping all of this information organized. So I'm not trying to do too much at once. But if you don't want to use it, you don't have to use it. First row of my table, though, is going to be just what my intervals are going to be. The second row, I'm going to do the 3x, because that's what's inside my function. So 3 times 0 is this, and that'll give me pi over 2, and pi, 3 pi over 2, and 2 pi. I multiplied everything in my top row by 3. That's all I did. Next, I'll find sine of 3x. Again, knowing the unit circle helps this stage go a little bit quicker, because if I know that sine is asking for my y values, then when I'm looking at sine of 0, I know what the sine of 0 is. It's 0. And pi over 2 is 1, and 0, and -1, and 0. Now, for our last problem, we would have been done here, because that's what our function is. But our function isn't sine of 3x. Our function is -2 sine of 3x. So I have one more row where I take everything in the row above and multiply it by -2. 0, -2, 0, 2, 0. Now I have my ordered pairs. My top row are my x values. My bottom row is my y values for plotting and graphing this on my plane. And there is my table with my picture. Going from 0 to 2 pi over 3. And some of you may be looking at this and asking, well, wait a second. All of our other sine ones started by going up and then coming down. But this one goes down and then goes up. And that has to do with the fact that we have a -2 out in front. That negative is actually a reflection over the x-axis. Again, another translation that you learned in college algebra in chapter 2.5. So because it's negative, all of this stuff that would have been up top flips down and is now on bottom. if you understand the translations from the college algebra, it does help you to see how these are going to be graphed moving forward. So this one had both. It had stuff that affected our amplitude, it had stuff that affected our period. But we were able to take it bit by bit to get our graph out. Are there questions on this one, on any of the steps that we did? Okay, I think I've got one more. Yep. Because if we're going to do a slightly more complicated sine problem, we should do a slightly more complicated cosine problem just to even things out, I think. Graph y equals -3 cosine pi x over 1 period. This one's a good one. Sorry, I forgot I zoomed in a little bit. Because if you're looking at it, our b in this case isn't a whole number or a fraction like we've been dealing with. The b in this one is pi, and that's okay. We can do that. It just changes our intervals a little bit. So the first thing we want to find is the period of our function. That's 2 pi over b. Well, the b in this case is the pi, so we're going to have 2 pi over pi, which means our period is just going to be over 2. The amplitude is the absolute value of a. The a in this case is -3. So we have some horizontal shrinking with our period because 2 is going to be less than 2 pi. And then we also have some vertical stretching with our amplitude. And then just like with our last one, since there is a negative down there, you can imagine that we are going to be reflecting that over our x-axis, which means instead of it starting up top, it's actually going to start down below. Now we need to divide our period, which is 2, into 4 parts. This is a little bit easier because we don't have to think about it with the pi at all. We're just dividing 2 into 4 equal segments, so we're going to have 0, 1/2, 1, 3/2, and 2. So our second row of our table, if you're using the table like I am, is going to be pi times x, because that's what's inside of our function. Next one would be cosine of pi x. So cosine of 0 is going to be 1. Cosine of pi over 2, that's 90 degrees, would be 0. -1, 0, and 1. Last row, we'll take -3 cosine of pi over x. That's where we get -3, 0, 3, 0, -3. So when x is 0, -3 cosine of pi over x would be -3. So it starts down low, and then it's going to rise up and come back around. I feel like the graphs, at least the ones that I present, while they might be nice because they're on graph paper, they're a little bit deceptive because I set my spacing up the same regardless of what my actual intervals are. That's mostly just to graph so that you guys can read it. But really what happens is if we were to graph all of these together, like on the same Cartesian coordinate system, you'd see more dramatically what's happening with the stretching and the shrinking vertically and horizontally. You would see that it's actually really smushed together, really spread out. So I think you'll see that a little bit more through your homework and your quiz for this section.